Hi everyone. Today's topic is about dummy variable and interaction effect. Actually, we covered this dummy variable topic a little bit last time. So we have two kinds of variables, right? Categorical variable and continuous variable. And dummy variable is a special form of categorical variable. So usually categorical variable has multiple categories to choose in terms of respondents, right? So there are options to choose. So are you a white, are you a black, or are you a Hispanic, or are you Asian? And then you have one option to choose usually, right? And then options are 4 at that time. Basically speaking, this is a kind of very simplified example. At that time, the categorical variable can be made 3 different dummy variables. So if you have only one option, only 2 options, are you a black? Yes. If you are not a black, then you say no. So black and others. That is one dummy variable. Are you a white? And non-white. So white and all others. So that is the second dummy variable. And are you a Hispanic? So Hispanic versus non-Hispanic. So that is a third dummy variable, right? So we're gonna make dummy variables from the one single categorical variable today, all right? Okay, so let's read one by one here. So 4 subgroups are located in one categorical variable. Okay, multi-category factor. So we have to change the categorical variable into multiple dummy variables, okay, to have the benefit of convenience of a dummy variable. First, a dummy variable is dichotomy. Dichotomy means just 2 options, 0, 1. Okay, so 0 is reference group, 1 is focal group. So here, gender or sex variable, so female or male. So in this study, female is coded as 0 and male is coded as 1 focal group. Okay. So whether or not female is reference group, it's all about your research decision making, research question. So if your focal group is female, you still can code female as 1 and male as 0. If your focal group is male, if your research question is focused on the male, then you code male as 1, female as 0. So this is a simple regression form, right? And then X is a dummy variable. So female or male. Female is 0, male is 1. So you have 2 options. So if you plug 0 for female here, this term will be eliminated. So Y hat becomes B0. If you plug 1 as male in this X, then you have Y hat equals B0 plus B1. Okay. B1 represents the predicted change in Y associated with 1 unit increase in X. So whatever the X unit is, B1 represents the predicted changes in Y associated with 1 unit change in X. So it's not scale-free, right? So B1 is unstandardized coefficient. Do you remember that? Okay, so 1 point change occurs in X. Then a change of B1 would change in Y. But when X is a dummy variable and only 2 occasions, female 0, male 1, so a difference of 1 point can only occur when X is equal to 1. Okay, when X is 0, the subject is female, but when X is 1, the subject is male. The slope B1 for our bivariate regression, where X is a dummy variable, equals the mean difference between the two represented groups. For this X, the slope B1 is the difference between the means of males and females. So plug 0 here for female, then this is removed. So Y bar for female becomes B0. And if you plug 1 for X, then B0 plus B1 is Y bar for male. So if you B0 plus B1 minus B0, then the leftover is B1. So B1 is mean difference between male and female in terms of Y. Okay, let's read this one. B1 is mean difference between male and female in Y. B0 is the intercept. B0 represents the mean of Y for the female as a reference group because you plug 0 for female. It is easier to see this empirically by running descriptive statistics and a t-test on 2 groups. Okay, so this is a simple regression and we have no other X factor. So in this case, F-test and t-test is gonna be the same, right? So t squared is the same as F. Anyway, before we move on that statistical analysis, let's see this descriptive statistics table. And this is NELS data. So public school is coded as 1, private school is coded as 0. So the mean of public school is minus 0.9 and mean of private school is 4.9. Very big difference, right? This is just the difference between, this is just the naive difference between private school and public school without any other factor. Just the mean difference, this is just the difference between private school and public school. And also, we have more scores of public school here. Look at the sample size. Before we move on, let me summarize the important regression assumptions. Okay. Model specification is about X and Y relationship. Linearity is also related to X and Y relationship. We checked linearity violation using scatter plot. Independence has 2 dimensions, right? One is data pair independence. Are they siblings, family members, or couples, you know, twins or whatever, you know, not independent people exist in your data set. The data collector knows that. This is about data collection structure. Another independence assumption is related to residual. IID assumption, do you remember that? EI tilde N parenthesis 0 sigma squares E parenthesis IID. So residuals are identically independently distributed normally with mean 0 and sigma square. Sigma square is a constant, fixed number homogeneity assumption, right? Equal variance assumption. So independence, if you just say independence assumption, then you have to think about two things. One is a data pair, the other is a residual assumption. Unfortunately, we do not have an independence assumption statistical test. We do not know if independence is violated through the statistical test, like a t-test or f-test. We cannot know the independence is violated through that kind of statistical assumption. Normality histogram or PP plot. Normality also two kinds. Joint distribution, X and Y, normal distribution. X should normally distributed, Y should be normally distributed. But residuals also normal distribution. So IID, identically independently normally distributed. Okay, so normal distribution has also two kinds of types. Homogeneity is a residual assumption. So residual plot, you remember that residual predicted standardized residual on the x-axis, and then residual standardized values, y-axis. And then it should have like a rectangle, because on the y-axis, between -3 and +3, the residuals are supposed to be equally located. So it looks like a rectangle, you know, not like a specific, like a type of curve, you know. So homogeneity between -3 and +3. I mean, some people kind of more liberal area of the discipline, and some people choose -4 and +4 spread evenly. And multicollinearity is a high correlation among X variables. So multicollinearity, tolerance, VIF. You know, in the beginning we look at the bivariate correlation metrics, and then we can find out high correlation among the X variables. And even though we didn't cover the VIF tolerance, these values are the index for detecting multicollinearity. So if you choose these two options in the SPSS, it will show the table about VIF and the tolerance, so you can find out whether or not it is a multicollinear collinearity issue is there. It's not that important, because we manually know, we can know that through the bivariate correlation. Okay. All right. So note, most observational study data violate the independence assumption. So this, in other words, selection bias exists. So here, correlation between X variable and a residual equals 0. Correlation between residual 1 and residual 2 equals 0. So this is independent, like no correlation among residuals. So we might have this satisfied if your data is really collected randomly. But you cannot avoid, I mean, your data cannot avoid this situation. Let's think about it. What is this meaning? Let's say that you already know some reasons are poorer than the other. You already know some race ethnicity groups are poorer than the other. What does that mean? So poor, the rich, the poor, this is income. So the meaning that region or race ethnicity groups are correlated income means non-zero correlation between race, ethnicity, and income, or the region and between the region and the income, right? So your residuals are not free from the selection of X in your mother. So that's why I put this one. Your data set, your mother, I mean your mother can be better. There's no absolutely correct mother, but your mother can be better than the other if you consider this factor. Okay, so when you model your idea, we have to read the literature review really thoroughly and then find out what kind of X variables are conflicted each other or intercorrelated each other. So we have to set up your the model based upon that kind of theoretical assumptions, and then you can have a good model. Okay, if you are if your data is really randomization, if your data is really randomly assigned, then maybe you can achieve this level. However, it's impossible for you to have this level. Yeah, there's no non-zero correlation between X variables and residuals. As I said, the examples, the interaction between region and the income, interaction between race and income. Okay. All right. So observational data, including the variables of subgroup, has a selection bias, yes. Regression using survey data, no causation when selection bias exists. Causation under a laboratory experiment versus correlation regression. Then what are we going to do when selection bias exists? So we need one more technique in addition to multiple regression. So the quasi-experimental design. I mean, we are conducting a study in terms of social sciences, and well, we still can conduct multiple regression, but they are just all about association, not causation. So if you want to say kind of causation, I mean, it's not necessarily 100% causation, but it's closer to causation, then you want to add some kind of quasi-experimental design techniques in addition to multiple regression, because we do not want to have a non-zero, too high correlation between X and residual. That's totally selection bias exists. So yeah, so correlation, we have to think about the meaning of correlation and causation. And a lot of scholars are conservative. Why? There's no absolute, absolute truth, or there's no absolute truth. So we try to reduce the selection bias. So when we talk about cause and effect, unless you conduct experimental design, you really need to be cautious in wording what you are doing, in the research. Okay. All right. Concept of dummy variables in multiple regression. So here, Levin's test for equality of variance. So far, we looked at the residual plot, scatter plot between predicted standardized residual and the standardized residual. So as long as it looks like a rectangle evenly spread dots, then we assume that is satisfied in terms of the homogeneity assumption. But that is just eyeballing method, quick and dirty. Once you have this table, then Levin test is a statistical test for homogeneity. So what is the null hypothesis? Sigma square is equal to 0. If you have multiple groups in it, every group's sigma square variance is going to be the same as the other group's sigma square. So as long as they are equal to each other, it is equal variance. So we do not want to reject the null hypothesis. So don't feel confused with this Levin's test with other types of t-test. You know, here t-test, confidence interval here, and t value is here. This is totally different from this, okay? So Levin test is for assumption violation checking, in particular with the homogeneity assumption. So we do not want to reject this null hypothesis. If we reject the null hypothesis of homogeneity assumption, then it is heterogeneous, not homogeneous. So we do not want to reject the null hypothesis. So alpha is the same, 0.05. So this p-value is larger than 0.05. So we fail to reject the null hypothesis. Okay. So since this p-value is larger than alpha value, we are okay with the homogeneity assumption in this result. Okay. And then second step is we go to t. So let me bring on idea of that you have learned in PUAD 628. Do you remember the rule 68, 95, and 99.7 rule? Yeah, so yeah, if you don't remember that, just Google it. 68, 95, and 99.7 rule. Then you'll find percentage. I mean the probability, percentage, and test the value, something like that. So here, t-test value is minus 11.9 degree of freedom. Okay, since this is satisfied with homogeneity assumption, we interpret this first row. Okay, don't think about this one. So here we try to find the p-value first, but it doesn't show p-value here. Then we have to choose two different ways. First, t-test value is here. This is larger than critical value 1.96. So when you have a t-value 1.96, your data belongs to 95%. So this 95% is from the rule 68, 95, and 99.7% rule. Yeah. Well, anyway, well, it's okay. For this moment, it's okay. Even though you don't understand the 68, 95, and 99.7% rule right now, what you need to know is here, t minus 11.969 is larger than the absolute value is 1.96, which is similar with the 2. So when you have 1.96 on the t, your percentage is 95%. Probability is 0.95. Okay, so this is statistically significant if this t-value is larger than critical value 1.96. And I'm talking about absolute value, then it is regarded as statistically significant. Okay, here p-value is here. P-value is here, so this is statistically significant. The result is consistent with this. Okay, the third method, whether or not we find out hypothesis testing, is a statistically statistically significant. Here, 0 is not captured in the confidence interval. So in that case, we conclude it's statistically significant. If this confidence interval contains 0, then we fail to reject the null hypothesis, which is statistically insignificant. The box shows the slope equal the mean difference from the descriptive stat, page 5, and t statistic minus 5.917 equals this value minus this value. The circle shows the value of the t-test, or the slope equals the 2-sample t-test. Also, the intercept equals the mean of the reference group. So the reference group is a private group. This is mean. And from this mean, if you subtract 5.917, then you will obtain the mean of the public school. And t-statistic, we do not evaluate this one. Okay, so this t-test, what is the null hypothesis? Yeah, public school is different from private school. The mean of a public school is different from the mean of the private school. That is the conclusion, because null hypothesis is the same means between two schools. Null hypothesis is mean of a public school is the same as mean of a private school. Since this is smaller than alpha 0.05, we reject the null hypothesis. So the conclusion is the mean of public school is different from the mean of private school. You might wonder why statisticians do this way, because you already know the private school mean is this, and the public school mean is this minus this. So you already know the two different types of schools means are different. Why do you do that? So this is just the descriptively, descriptive summary. We want to know how much this is, how confident we can say this. We want to show the percentage. We want to show the probability with the confidence level. That's why we did that. And statistically significant means, even though there is a kind of random error happen, the case, the means are the same, can happen, but it's not very common. It's below 0.05 criterion alpha. That's why we do the two stages in order to conclude whether or not the mean of public is different from the mean of private school. Okay, if you just show this difference only, then there is just a mathematical approach. If you show how different, with what kind of possibility, that is a statistical approach. Get it? That's why we do the statistical test using t-test, okay? Be careful though, the above result only hold exactly for a dummy variable coded with 0 and 1. If the dichotomy is coded with numbers that are not 1 unit apart, then the slope will not equal the mean difference. You can check this by running regression using a dummy variable that represents two groups with numbers other than 0 and 1. So we don't need to do it because we already know the convenience of the reference group coded 0. Suppose now we have three groups level, say urban, suburban, and rural. So we have three categories, three options. So in that case, we have to make two different dummy variables. So urban and non-urban, and suburban and non-suburban, something like that. If we include G10 urban, so G10 variable has three options: urban, suburban, rural. And then if you see the variable view in the SPSS dataset, then you will find out one is coded urban, two is coded suburban, and three is coded rural. Multiple regression will treat it as if it were a number. Okay, 1, 2, 3 here are not number, even though it looks like numerical value. You know, 3 does not necessarily mean higher than the 1 in this case. You know what I'm saying? This is just simply called nominal value, nominal variable, rural, suburban, urban, okay? But SPSS is a machine, so he does not know that. So what we want to do is we have to change that into dummy variable, and then we can keep using the same tab, regression. If you don't want to change this into a dummy variable, then you shouldn't use regression, but you can have other function in the SPSS. We do not, manually change the categorical variable in dummy variables if we use other function. Yeah, it's not necessary, so it's more convenient. So I will tell you about that shortcut later. But in this lesson, I'm just talking about the conceptual things rather than procedure or knowledge about SPSS. So just to focus on this in terms of conceptual perspective of the dummy variable only. Okay. So anyway, SPSS treated as like numerical value, not nominal value. So we have to be careful when we try to use the regression function. So is a subgroup, so is a suburban group X2 twice as good as an urban one? No, right? So that's not the numerical meaning, yeah, like that. Okay, so SPSS machine does not stop you from using a categorical variable in regression, as if the X variable is a continuous numerical variable. Here is output using G10 urban to predict teacher community, which is wrong. So we shouldn't fall in this kind of mistake. Okay, G10 is a nominal variable. 1, 2, 3 categories: urban, suburban, and rural. That doesn't mean each number is 3 is higher than 2 or 2 is higher than 1. That's not it in this case. So if you just conduct the regression using regression function in the SPSS, you will have this same table, which is not right. So what we are going to do in order to use regression tab, we're going to manually change the categorical variable into two different dummy variables. So when you see urban and G10 variable, G10 urban variable, you will see 1 was coded 1. but now you're gonna have two different dummy variables in the data set, and when you create two different dummy variables, you can make the names like urban X, suburban X,